Viscous flow. Viscous flow refers to the flow of a fluid that experiences internal friction and resistance to the motion. In this type of flow, the fluid particles move at a different speed and adhere to each other, resulting in the transfer of momentum and energy between adjacent layers of fluid. Viscous flow is characterized by presence of shear stress, which is the force per unit area acting parallel to the direction of flow. Example of viscous fluid are honey, syrup, and motor oil.
Inviscid flow is a fluid dynamics concept that simplifies fluid flow analysis by avoiding internal friction or resistance to motion. It is commonly used when viscosity effects are negligible or ideal fluids are studied.
Shear stress. Viscous flow is characterized by the presence of shear stress, which is the force per unit area acting parallel to the direction of flow. It is responsible for the resistance to fluid motion and the transfer of momentum between adjacent fluid layers. Velocity gradient. In viscous flow, the velocity of the fluid particles varies across different layers. This velocity variation creates a velocity gradient, where fluid particles closer to the boundary move slower than those in the center of the flow. Energy dissipation. Due to internal friction, viscous flow results the dissipation of energy. This energy dissipation is responsible for the conversion of mechanical energy into heat, which can lead to a decrease in the fluid's kinetic energy. Boundary layer. In viscous flow, a thin layer called the boundary layer forms near the surface over which the fluid is flowing. This boundary layer experiences the maximum effects of viscosity and plays a crucial role in determining the overall flow behavior. Flow resistance. Viscous flow exhibit higher resistance to flow compared to inviscid flow. This resistance is due to the internal friction and the transfer of momentum between adjacent fluid layers.
No shear stress. In inviscid flow, there is no shear stress or frictional force between adjacent fluid layers. The fluid particles move without any resistance or transfer of momentum, resulting in a smooth and continuous flow. Irrotational flow. In inviscid flow, the fluid particles move in a way that preserves their vorticity, meaning there are no vortices or swirling motions. This is known as irrotational flow. Potential flow. In inviscid flow, the flow field can be described using potential flow theory. Potential flow assumes that the fluid is non-viscous and incompressible, resulting in simplified mathematical models to analyze the flow behavior. Conservation of energy. In inviscid flow, there is no energy dissipation due to internal friction. The total mechanical energy of the fluid, consisting of kinetic and potential energy, remains constant along streamlines. Streamlines. In inviscid flow, the fluid particles follow smooth and well-defined paths known as streamlines. These streamlines can be used to visualize and analyze the flow behavior.
Viscous flow is characterized by shear stress, resistance to fluid motion, and momentum transfer between layers. It results in energy dissipation, converging mechanical energy into heat and forms a boundary layer near the fluid surface.
Inviscid flow. Inviscid flow has no shear stress or frictional force between adjacent fluid layers. Fluid particles move without resistance or transfer of momentum, resulting in a smooth and continuous flow. In inviscid flow, fluid particles move in a way that preserves their vorticity, resulting in a rotational flow. Inviscid flow can be described using potential flow theory, assuming the fluid is non-viscous and incompressible. There is no energy dissipation due to internal friction in inviscid flow. Fluid particles in inviscid flow follow well-defined paths known as streamlines.